In this video, I want to talk about an actual example doing epsilons, proving that a sequence converges, in this case, to 0. So I want to take the sequence that we had before, I to the n over n factorial, where n starts at 0, and we're going to show that the sequence converges to 0. And so just a little bit before we get into the actual proof, there's a few different ways that we can write this. You can write that this is the limit as n goes to infinity of the sequence, I to the n over n factorial. You can write that this is the limit as n goes to infinity of a sub n, where a sub n is the sequence above. So that's basically saying the same thing. Or there's this other notation, a sub n goes to 0. This kind of just is a nice succinct way to write that the limit of a sub n is 0 as n goes to infinity. Here it's clear that since we're talking about a sequence, we're worried about the behavior as little n goes to infinity, and that's going to go to 0 as little n gets large. So that's the idea. And so what we're going to do for our proof is the following. So so let's let epsilon be given. And then I always just like to write this out. We want to find a value capital N so that if little n is greater than or equal to capital N, then our sequence a sub n minus the limit, which in our case is just the complex number 0, is less than epsilon. Okay, so off to the side, I want to do a little bit of algebra. So I want to do a little bit of algebra, and then probably we'll, this is the typical epsilon delta stuff or epsilon n stuff. We'll do a little bit of algebra. We'll erase it, pretend like we didn't do it, and then we'll have these magic values of capital N. It's kind of a backwards way to write this, but that's okay. And so notice that the modulus of I to the n over n factorial minus 0 is just 1 over n factorial. And 1 over n factorial is going to be less than or equal to 1 over 2 to the n if n is at least 4. Okay, so if n is at least 4, then everything is fine, and n factorial is greater than or equal to 2 to the n. So n factorial is greater than or equal to 2 to the n if n is at least 4. And therefore, when you reciprocate, you get 1 over n factorial is less than or equal to 1 over 2 to the n if n is at least 4. Okay, and then 1 over 2 to the n is going to be less than epsilon if n is, let's see, this is going to be the equivalent of saying that 2 to the n is greater than 1 over epsilon, which is the same as saying n is greater than the natural log of 1 over epsilon divided by the natural log of 2. Okay, so n has to be at least that big. So what we can do is we can take capital N to be the larger, so the maximum of 4, and the natural log of 1 over epsilon divided by the natural log of 2. Okay, and then in that case, we always have our inequality that we want. This is always going to be less than epsilon, and then we can just show that in that case, 1 over n minus n factorial minus 0 is going to be 1 over n factorial, which is going to be less than 1 over 2 to the n, which is less than epsilon. Okay, and there we go. I don't actually care about whether capital N is an integer or not. I can't remember what the book said about whether capital N is an integer or not, but it doesn't matter. Whether you want capital N to be an integer or not doesn't matter, because what we're saying is that eventually the sequence is such that the terms minus the limit are as small as you want them to be. So if this happens when capital N is, say, 25.4, say for all little n greater than or equal to 25.4, I just pulled 25.4 out of thin air, then you could either pick capital N to be 25.4, or if you insist that capital N is an integer, take capital N to be 26. I don't care. Round up to the nearest integer. And if you can find a non-integer that does the job, then there's an integer that does the job, and vice versa. So it actually doesn't matter whether capital N is an integer or not. Okay, but here's an epsilon n example where we actually go through and do the details there.